Okay. So one of the main things we did last time is we applied this, defined this Cazul differential, which, just like the exterior derivative d, is a way to make one definition that at once encompasses grad, div, and curl on higher order analogs. This is one definition kappa that at once encompasses multiplication by x, dotting with x, crossing with x, and higher order analogs. And one advantage of doing that is you remember one formula, and it's actually lots of formulas in different contexts. And with Cazul, there's really only one very important formula, which is this homotopy formula, where d kappa plus kappa d is the identity, but it's scaled, and how it scales depends on the homogeneous polynomial degree and the form degree. So that, now let's go back to a question asked before. So as one example of the question would be, suppose we're given a, I don't know why I said 3 here. So, say we're in 3D and we give an rth degree polynomial vector field. So we have a vector field of r, we have 3 polynomials of degree r, and the divergence of that vector field is 0. Of course, it's a curl of something, but is it a curl of a polynomial of degree r plus 1 vector field? So that's a calculus question, right? Polynomials and calculus. And that will come out of this. More generally, suppose we take the polynomial de Rham complex. And so now we take a polynomial differential form for which d is 0. Is that d of a polynomial differential form of one polynomial degree higher? Okay, and now we'll prove that. Well, the proof is totally trivial with the Cazul complex. The Cazul complex is the complex that goes backwards. It has the same spaces, but it's now the kappa goes in the other direction. And actually, in order to do it, because we have that scaling by homogeneous degree, I should use homogeneous polynomials here, and then we can add them up. So basically, you apply the result to all the homogeneous terms of a given degree r. So here's a homogeneous Cazul complex. Okay, and so now I take a p in polynomial, well, let's say I take a p in polynomial k forms, and dp is equal to 0. And then I want to show that there exists a u in polynomial of degree 1 higher, but homogeneous, of degree 1 higher, k minus 1 forms, such that du is equal to p. And all I do is I use the homotopy formula and say, well, r plus kp is equal to d kappa p plus kappa dp. That's the homotopy formula. But dp is equal to 0, so this is gone. So that says that p is equal to d of r plus k inverse kappa p. So not only do I prove that p is d of something, well, this is, if p is a degree r k form, then kappa p is a degree r plus 1 k minus 1 form. So not only is p a d of an r plus 1 kappa minus 1 form, but I have the formula for it. Except for the constant in front of it, it's just kappa p. Basically, p is just d of kappa p, if d of p is 0. Because the homotopy formula says that p is just d kappa plus kappa dp. So that proves that this sequence is an exact sequence, meaning there's no homology here. The homology groups are 0 all the way across here, and then the homology groups is a constant here. The reason the constant doesn't satisfy the same argument as r plus k is 0, so you can't divide by it. Okay, that same proof shows that the homogeneous polynomial de Rham complex is exact. Then adding them together, the polynomial de Rham complex is exact, and also the same thing for the Cazul complex. where the only place there's homology is the constants over here. So that's one important consequence of the homotopy formula, but there's a lot of others. So this is a useful relationship. Kappa, when applied to a boundary, kappa of d of something, is it's 1-to-1. Kappa of d omega 0 means d omega is 0. Kappas do not, there's no kernel, the kernel of kappa does not include any boundaries. How do we know that? Well, kappa d omega, suppose this is 0, then, let's see what's the best way to do this. Then I have omega is equal to kappa d omega plus d kappa omega times a certain constant. And kappa d omega is 0. And what am I trying to show? That maybe I have to do it, I guess I probably have to say d omega, which is equal to a certain constant times d omega is d kappa d omega plus kappa d kappa d omega plus kappa d omega. We're assuming kappa d omega is 0, so this is gone, and d of d is always 0, so d omega is 0. Okay, and the same thing shows that d is 1-to-1 on kappa, since this whole thing is symmetric. So that tells me that all K forms, homogeneous polynomial degree R K forms, breaks up into kappas and d's. Let's just see that clearly enough. So the claim is that you take a degree R K form, and you can write it as D of a degree R plus 1 K minus 1 form, and kappa of a degree R minus 1 K plus 1 form, and that this is a direct sum, nothing in the intersection except for 0. So first of all, how do we know everything in here can be written as something in here and something in here? That's the homotopy formula. Up to a constant, omega is equal to C d of kappa. It's equal to d of some constant times kappa omega plus kappa of d of constant times kappa of C d omega. So I've put the constant over there. So this shows that everything in here is a d plus a kappa. So it's in here plus here. On the other hand, is it possible that we have d of some u is equal to kappa of some v? Well, then we have d kappa v is equal to d du, which is 0. So kappa v equals 0, because d is 1-to-1 on kappa. And similarly, kappa du is kappa v is 0, so du is 0. So this thing is 0. I guess I only need to show one of them is 0 since they're equal. So this is a direct sum. So the homotopy relation shows us that K forms split up into D's and kappas in a direct sum. Okay? So now I'm going to use that direct sum to define a new space of polynomial forms. If I take, we had the space already, PR lambda K. And of course, PR lambda K is PR minus 1 lambda K, plus you add on the homogeneous things of degree R to make it PR lambda K. Polynomials of degree R are polynomials of degree R minus 1 plus extra homogeneous of degree R in a direct sum. But now the homogeneous of degree R part breaks into two pieces according to this formula. So I could take PR minus 1 and only add one of those two pieces, only the kappas, not the D's. And I get a space which lies between PR minus 1 and PR. If I added the kappas and the D's, I'd get up to PR, but I threw away the D's. So I get something smaller, and therefore we call it PR minus lambda K. Okay? So we've added to our repertoire of spaces of K forms, we have PR lambda K, and now we also have PR minus lambda K. These will turn out to be the two spaces that are used for finite elements for K forms. Some observations. If we're talking about 0 forms, this part is gone because there are no -1 forms. So the kappa term is everything. So there's no difference between PR minus lambda k and PR minus lambda 0 and PR lambda 0. They're equal. So what this is going to mean is I'm not going to invent any competitors to the Lagrange elements. We're just going to invent another name for the Lagrange elements. You can put a minus there if you want, but it's the same old guys. If we go to n forms, it's the opposite. In that case, the kappa term is gone because there are no n plus 1 forms. So in that case, PR minus is PR minus 1. So again, there's nothing new. There's just a different name for it. Instead of calling it PR minus, we call it PR minus 1, we call it PR minus. So we have an equality there the other way. But in all the other cases, there are both d's and kappas, and this space is strictly contained between these two. We'll work out its dimension, and there's no equality there. So here's the dimension of PR minus lambda k. It's r plus n, r plus k, and times r plus k minus 1 choose k. You might remember the formula. Let's go back to the formula we had for the dimension of PR lambda k. That was r plus n choose r plus k choose k. And now this is r plus n choose r plus k minus 1 choose k. And so the ratio is r over r plus k, which shows you, in fact, when k is equal to 0, there's no difference, but otherwise it's a smaller space. Next is to look at the range of D on these spaces. And then the statement is that the range of D on the smaller space, PR minus, is the same as the range of D on the bigger space, full PR. Why? Because all I dropped out were some D's, and the range of D on boundaries is 0. D squared is 0. So I didn't lower the range of this space. So that's going to tell you that the PR space we tend to use after we apply D to it, then the complex gets us into PR minus 1 for the next space. The PR minus spaces, we could use the same thing, but we'll see what happens actually. Okay, how about the null space? What are the things in PR minus lambda k for which D is 0? Well, first of all, there's the PR minus 1 part has to go by D to 0. That's this. And then the kappa part has to go by D to 0. But we know D is 1 to 1 on the range of kappa, so that never happens unless the kappa part is 0. So the null space of PR minus lambda k is the same as the null space of D restricted to PR minus 1. Okay, and now we get a complex that's a little bit like this polynomial de Rham complex, but now with the PR minus spaces. D of PR minus, so the PR minus 1 part goes into PR minus 2, and what about the D of the kappa part? Well, this is, let's see, we probably have this up here somewhere. The range, okay, so the range of PR minus is the same as the range of D on PR, so this is PR minus 1, inside PR minus 1. So this actually maps to PR minus 1, but I'll increase it up to PR minus, so that this space certainly maps into here. And then since these are both the same R, that maps into the next one. And so this is a complex. And let me show you that it's an exact complex, that we haven't added too much here, that the homology is still 0. So what do I have to show? That if U is in PR minus lambda k and du equals 0, then U is equal to D of some V in PR minus lambda k minus 1 with the same R. So let's see what happens. If U is in, I think we must have it all up here. If U is in PR minus and in the null space, then it's in the null space of D on PR minus 1. That means by the polynomial de Rham complex, so V is in PR minus, V is in the null space of D restricted to PR minus 1 by that line there. Therefore, V is, U is equal in there. So therefore, U is equal to dv, where v is a polynomial of degree r, k form, because in this complex you go up. If you're in PR minus 1 and d is 0, then you're d of something in PR. So this u is d of something in PR, but the range of d on PR is the same of the range on d on PR minus, so we can take the v in PR minus. So that shows that this complex here is in a complex with no homology. If you're in here, D maps you in the next space, and the null space is only the things that were D from the preceding space. So we have these two complexes, which are very important to remember. The polynomial de Rham complex. You can do them either homogeneous or the full polynomial space. Let me go back to the full polynomial space. So you can take a polynomial of degree R0 form, D of is a polynomial of degree R minus 1 form, and so forth down to PR minus n. Or you could start with a PR minus 0 form, which is actually the same thing because minus doesn't mean anything for 0 forms. And D, and you get a PR minus 1 form with the same R, and D and so forth to PR minus n form. And both these complexes are exact. No homology except for the constant, the obvious constants. Okay? These spaces are much bigger here. These are the big spaces because this R keeps going down. Okay, clear? So what am I doing here? I'm defining some spaces of polynomials. These will be used as the shape functions to make finite elements. So we'll be using piecewise polynomials where the pieces will be either in the PR lambda k space or the PR minus lambda k space. Okay, the next comment is actually there are sequences in between these two. These are not all the sequences. And you just reason in the same way. All you need to know are these two statements about how the ranges of a PR minus is the same as the ranges of the next bigger PR, and the null space of the PR minus, same as the null space of D on the next smaller PR. And what that tells you is that if you want to build together a complex, if you're taking D, you can view it as mapping into PR minus or PR minus 1. D of PR is into PR minus 1. It maps into both of these spaces, but the null space of the next D is the same. So since we know the bottom one is exact where the PRs goes down, then it would also be exact if you use this PR minus. Similarly, if you're in a PR minus space and you take a D, you can see it as going into the next PR minus. That's the second sequence over there. But you could also think of it going into the smaller space PR minus 1, and the null space of D on these two things is the same, so that you'll get an exact sequence also. So taking into account the fact that at the beginning the spaces are the same, so you don't have any choices for the first space, you always start with PR lambda 0, whether you call it PR or PR minus. Then you have a choice and another choice, and you have n minus 1 choices. So you actually get 2 to the n minus 1 possible sequences in n dimensions, and they're all exact. The top one here is the PR minus sequence. This first space is really just, it could be called PR minus, and the last space could also be called PR minus. So this is the pure PR minus sequence. And the bottom sequence is the pure polynomial de Rham sequence, PR, PR minus 1, PR minus 2, PR minus 3. And then the other choices are in here. And actually in Rick's talk, when he was using two versions of the de Rham complex to make the elasticity complex, he used the top one here and the second one, I believe, either the second or the third. I think the second. Okay, so we have spaces of shape functions, the k forms, and they combine into complexes. And now we have to make finite elements, so we need not only shape functions, but degrees of freedom. And that'll finish the definition of a finite element space. So I'm going to first define the PR minus family of simplicial finite element differential forms. So it's an incredibly all-encompassing construction in the sense that you go into any number of dimensions, take a simplicial measure, 1 dimension, 2 dimensions, or any more, or any number. Then you pick any k-form degree, 0 forms, 1 forms, up to n forms. And you pick any polynomial degree, 1, 2, 3, as far as you want. For all of those, you can define a space PR minus lambda k on a simplicial mesh with one definition that covers all the cases at once. The shape functions, of course, are on each simplex t. You take these polynomials just described, PR minus lambda k of t, which are polynomials of degree r minus 1 k-forms plus things of the form kappa of a polynomial of degree r minus 1 k plus 1 form. And then the degrees of freedom are given by this formula, which is very similar to the formula we had for Lagrange finite elements. On a face f of dimension d, you take the trace of the function and you wedge it with a d minus k form. Why a d minus k form? Well, this is a k form and this is a d minus k form, so if you wedge them together you get a d form, which is the only thing that you can integrate over a d-dimensional simplex. So you don't have to remember that's d minus k, it's the only thing that makes sense. And then, just like for Lagrange elements, the higher the dimension of the face, the lower the degree of the polynomials you use as weights here. And so you would expect that whatever degree you have here, it would be decreasing in d as it is. And the only question is, why does it start with r, when d is equal to k, it starts with r minus 1. Why is that the natural place to start? If I tell you that, then the formula is very memorable. You can just figure it out. And this is one of the things that sold me on this, because before this, if you asked me, by the way, what are the degrees of freedom for the Nedelec cubic face element in 3 dimensions of the first kind, I wouldn't have remembered. I would have to start searching through the literature. But here, that's the formula, and it covers all of them. So let's look at this formula. So the thing to remember, okay, and this is an important point also, is you notice that the shape functions we're using are PR minus. The weighting functions we're using, the degrees of freedom, are PR without the minus. Okay, that you have to remember. For the PR minus spaces, you use degrees of freedom that are weighted by PR spaces, and it'll be vice versa. Okay, so if you can remember that, then you know the degrees of freedom are going to have here Q and P, no minus, something, lambda. And here we decided there's no choice except for d minus k, so we get a d form over the face, where f is a face of dimension d. Of the triangle. Okay. Now one thing to think about is you start, the d has to be greater than or equal to k. 2 ways you could think about this, well, several ways. Since this has to be d minus k, and you get 0 if d were less than k. Anyway, you can't possibly be integrating a k form over a simplex of dimension lower than k. Wedging it will only make it worse. Okay, so then we go to the lowest dimensional faces, the k-dimensional faces. And we need to have this function be, we want to have it so that if we go to a k-dimensional face, here's the case k equals 1, k-dimensional face, we're going to have the polynomial on this side and the polynomial on this side. And since we want to have something in the domain of d, we want this to agree. So we want the same polynomial from here and from here. So we need, in other words, if this is t minus and this is t plus, the trace of u minus on f should be equal to the trace of u plus on f. That's the continuity we need to enforce with our degrees of freedom. Now, since the k-dimensional face is the lowest dimensional face that has any degrees of freedom, that means these degrees of freedom on the face have to ensure this. Okay, what kind of object is u restricted to this face? Well, u is a PR minus lambda k on t. So the restriction of u to the face is a PR minus lambda k on the face. It's easy to see that the restriction of the Kazul operator to a subspace gives you just the Kazul on the subspace. So now, this is a k-dimensional face, and this is a k-form, and we know that on n forms, on an PR minus n form is really just the same as PR minus 1. So here n is k. Since we have a k form on a k face, this is the same as PR minus 1 on the k face. So this is a polynomial of degree r minus 1, u on this face. So we have to weight it against polynomials of degree r minus 1 if d was equal to k. And then it goes down as d goes up, so then we add plus k minus d. And so then when d is equal to k, we get r minus 1, and it goes down. So so you can reason out what the degrees of freedom have to be. Nothing else makes sense. Okay, so we may take that reasonable choice of degrees of freedom, and we take these shape functions. And then, of course, there's a theorem to be proven. I did not work to make sure that the number of degrees of freedom was the dimension of this space and that they're unisolvent. That has to be proven, just like it had to be proven for the Lagrange elements. And then, just like for the Lagrange elements, we saw the degrees of freedom were the right thing to impose the continuity so that the thing is in the domain of the exterior derivative. And that I did sort of, using the fact that I wanted to prove that, that's what convinced me I should put r minus 1 plus k minus d there. Okay, I'm going to go through the proof of this theorem, at least the first sentence. So we have to do a dimension count. So how many degrees of freedom are there? Well, for each face of dimension d, k or more, so this is the number of faces of dimension d in the n simplex. We used a weighting function of pr plus k minus d minus 1 lambda k on that d-dimensional face. So I have to take the number of such faces times the dimension of that polynomial space. The number of faces is, oh, this thing is going. The number of faces is n plus 1 choose d plus 1. And the dimension of the polynomial space is the degree of the polynomials plus the dimension of the RD, choose d. So r plus k minus 1d times, since they're k forms, there are d choose k components. This is the k forms, this is the polynomial space, and this is the number of these. Now I just do a change of the summation integral. Instead of d greater than k, I replace d by j plus k, and j is greater than 0. So n plus 1 choose j plus k plus 1, r plus k minus 1 choose j plus k choose j. Then I use the same two identities I used before, namely the trivial one, AB, BC is AC, A minus C, A minus B, which you just write out. And the second one comes from matching terms in the binomial expansion. And when you put those in and simplify, you get the number of degrees of freedom is exactly the dimension of PR minus lambda k. And I don't think I mentioned how we prove the dimension of PR minus lambda k, so I'll do that at the end. Or did I? Did I do it? Maybe not. Okay, so we know this set of degrees of freedom is the right number for the space PR minus lambda k. Then how do we get unisolvents? So we have to show if u is in PR minus lambda k and all the degrees of freedom are 0, then u vanishes. So just like in the Lagrange element case, we're going to reduce it to something that vanishes on the boundary. But it's a little bit different here. There's a small difference. So here's a lemma that can be proven just like in the Lagrange case. If you have a PR minus 1, not a PR minus 1, not a PR minus, a PR minus 1, lambda k, and it vanishes on the boundary of a tetrahedron, and it's orthogonal to PR plus k minus n minus 1, n minus k forms. Those are the things that makes sense here. That's a k form, that's an n minus k form, so I can integrate over the tet. If that's true, then this is 0. And I didn't write out the proof of this, but this is an explicit proof. You just write down a specific formula for q. This is the analog in the Lagrange case. We said that anything that vanishes on the boundary looks like lambda 0 dot lambda np, and we took q is equal to p. So there's something similar here. a little bit more complicated to write down. It gives that lemma. Okay, now using that lemma, it's not quite as easy as in the Lagrange case, but as you see, it's not too hard. And by the way, this proof is not in the literature anywhere. I think when I write it up in the book, it'll be the first place it's written down. Take a U in PR minus 1 lambda k for which all these degrees of freedom vanish. The traces of U, wedge Q for Q in those spaces. That's our degrees of freedom. Well, then the trace of a PR minus lambda k on a tet is the PR minus lambda k on the face, and the degrees of freedom also carry over, because the degrees of freedom only depend on k and d, on the d of the face, but not on n. So just like for the Lagrange elements, we have an induction on dimension, and we get that the trace has to vanish on the whole boundary. So we have no problem showing if all the degrees of freedom vanish, then by induction the trace vanishes on the boundary. And so what we need to show is if we have a PR minus that vanishes on the boundary, and it has these orthogonalities that were some of the interior degrees of freedom, then U vanishes. Unfortunately, this is not an exact match for our lemma. It is an exact match for our lemma for zero forms, but it's not an exact match for our lemma in other cases, because this is PR minus, which is a bigger space than PR minus 1. So how are we going to apply the lemma to this situation? We have a PR minus that vanishes on the boundary, and if we knew it was a PR minus 1, then we could apply the lemma and say it was 0. So we have to show it's a PR minus 1 and not really just a PR minus. And we have to do that using the degrees of freedom. So we invoke the homotopy theorem and say, well, if U is a PR minus and DU is 0, then it's a PR minus 1, because the extra kappas you add to PR minus 1 to get PR minus are not in the kernel of D. So you can't add any extra kappas. So it's enough to show du is 0, because then U would be a PR minus 1, and we could apply the lemma. So now we have to show du is equal to 0. Okay, U is a PR minus that vanishes on the boundary. Then du is a PR minus 1 that vanishes on the boundary. PR minus 1k plus 1 form that vanishes on the boundary. And what do we have for degrees of freedom of du? Well, you write down du wedge p. For a p in this particular combination, you integrate by parts, no boundary terms, because du vanishes on the boundary. And you get something that was in the degrees of freedom you had before, because you look at these guys and you look at dp, and that becomes one of these guys. So I won't go through all the index counts on it, but it works out just right. So you get that du is a PR minus 1 that vanishes on the boundary, and all its degrees of freedom vanish. So the lemma does apply to du, because that's about things in PR minus 1. So du is 0. But if du is 0, that means U was not really a PR minus 1. It was not really a PR minus. It was a PR minus 1. So the lemma applies to it as well. So it all fits together. That's the main message of it. And that one argument, in one fell swoop, proves unisolvents for the Raviart-Thoma elements, the Lagrange elements, the Nedelec face elements of the first kind, the Nedelec edge elements of the first kind, and all their generalizations in higher dimensions. So today I started at 12:30. Okay. Okay, there's a second family of finite elements, the PR minus spaces, and now there's a second one called the PR spaces. As you would imagine, the shape functions are the full PR lambda k's, not the ones that have the d's that have the extra kappas. And the degrees of freedom, easy to remember. The one thing you have to remember is the degrees of freedom for the PR spaces are the PR minus spaces. Then this d minus k is the only thing that makes sense. And for the same reasoning argument I used before, r plus k minus d is the only thing that makes sense. So this is what we would expect it to be. And then you have to go through, and again you count, and you find the number of degrees of freedom is the dimension, and they're unisolvent by virtually the same argument. So now we have a second whole family of finite elements that uses the full polynomial spaces. And now let me go to the examples. I mentioned them, but now let's go to them specifically. So this is sort of the periodic table of the finite elements. You have the PR lambda k's and the PR minus lambda k's, and you can vary the minus or not, and the R and the K and the number of dimensions, and you get sort of all the nice finite element differential forms on simplices that I know of. So first of all, the PR minus lambda 0 forms will do 2D. Those are the same as PR lambda 0 forms, and those are just the familiar Lagrange elements. For R is 1, they're the piecewise linears with 1 degree of freedom per edge. For R is 2, they're the piecewise quadratics with 1 degree of freedom per vertex, and 1 degree of freedom per vertex and 1 per edge. For R is 3, there is 1 degree of freedom per vertex, 2 per edge, and 1 in the interior. The PR minus lambda 1s is a special space. So for example, P1 minus lambda 1 is first of all P0 lambda 1, and then kappa of P0 lambda 2. So P0 lambda 1, these are like vectors with constant coefficients, so these are things of the form A comma B. And P0 lambda 2, well, this is a constant. What's kappa of, so lambda 2 is dx1 wedge dx2. What's kappa of dx1 wedge dx2? It's x1 dx2 plus x2 minus x2 dx1. Or as a vector, it's minus x2 comma x1. And we want constants, multiples of that, so plus some constant c times minus x2, x1. So that's the shape of, that's the vector proxy for the shape functions for P1 minus lambda 1 in 2 dimensions. So it's a 3-dimensional space of things of this form. That's the Raviart-Thomas space if you've rotated it so everything's tangential to the boundary. That's the Raviart-Thomas space in H-rot. So this construction has discovered the Raviart-Thomas shape functions, and now we have a name for them. They're P1 minus lambda 1. They have 1 degree of freedom per edge. Yeah?
I don't know what the answer is. Is there some relationship between these rotated Raviart elements and their Hodge star and the normal Raviart elements?
Yes. Let me think about that. I think the answer is yes. Well, was it? The question is there a relationship between the perp operator that you use to rotate the Raviart interpolants and the Hodge star operator? And I guess the answer is the following. Okay. So if you're in 2D, this is only a 2D problem, you have two choices of, these are like functions. So these are functions, say C infinity omega, and there's only one natural way to make that identification, but there's two ways you could identify this space with vector fields. One is alpha 1 dx1 plus alpha 2 dx2 goes to alpha 1 comma alpha 2. And the other one is it goes to minus alpha 2 comma alpha 1, which is alpha 1 comma alpha 2 perp. Okay, now each of the operations, D, kappa, Hodge star, and so forth, then can be interpreted as operations on scalar fields and vector fields. So of course one of these gives us grad and rot, and the other one gives us curl and div. As far as Hodge star, well, if you choose the top one, you get the perp operator as the Hodge star. If you choose the bottom one, I think you get the perp operator also, maybe with a minus. If you identify one side with the top one and the other side with the bottom one, you get the identity operator as the Hodge star like we do in all the other cases. So I guess that's the connection. And it's nothing special to rotated Raviart-Thomas, it's rotated anything. Okay, so The P1 minus space is the lowest order Ravi-Artoma, and the other PR minus lambda 1s are the higher order Ravi-Artoma spaces. So this is actually things where now A and B are polynomials of degree 1, and C is a polynomial of degree 1. Then that's the definition of the space Ravi-Artoma functions. Actually, if you read Ravi-Artoma's paper, they got the first one right, and the other ones they didn't have the right definition of the space. It got corrected later by Nedelec. It had many of the properties it should have, but it didn't have all the properties that we like to have. This definition came up with from Nedelec when he did generalize to 3D. Of course, he didn't use the Kazul operator, but he just wrote down this formula here, or the rotated version of that formula here. And what about for two forms? Well, those are L2 functions. All you get, in that case, there are no degrees of freedom on anything except in the triangle, so you get discontinuous piecewise polynomials. And we know that P1 minus is constants, P2 minus is linears, and so forth. So you get these guys, and these form nice complexes as you go across. The first one are the Whitney forms. 1 degree of freedom per vertex, edge, and triangle. And the D operator maps the first and the second and so forth in each case. Okay, that's the PR minus family in 2D. Here's the PR minus family in 3D. For 0 forms, you get the Lagrange elements, just as before, and the minus doesn't have any effect. For 1 forms, you get Nedelec's generalization of Ravi-Artoma elements to H curl, which are called the Nedelec edge elements of the first kind. And you get exactly those spaces. And for PR minus lambda 2, you get Nedelec's generalization of the Ravi-Artoma elements to H div, the Nedelec face elements of the first kind. And for PR minus lambda 3, you get the discontinuous piecewise polynomials of various degrees. And these all form nice complexes as you go across the slide. What about the PR families? Well, the 0 forms, they're the same thing. The minus doesn't do anything, so we get the Lagrange elements. The 1 forms, PR lambda 1, was invented in 2D by Brett C. Douglas Marini in 1985, where they said, you know, you could use the full polynomial space, but don't use the usual degrees of freedom that you use for Lagrange. Just use, well, they rotated it, so they said just use the normal component degrees of freedom, or in our case, the tangential component degrees of freedom. And so this is full vector spaces where both components are P1, so 2 components with 3 dimensions, so 6 degrees of freedom, and you take the tangential component along the edge, which is the P1, and specify it completely by giving 2 degrees of freedom. That's the BDM space, BDM1. And actually, already here you could see they didn't have such nice degrees of freedom as we have that fit in one simple formula. They were very concerned with having a commuting diagram between these spaces, but they hadn't thought about a commuting diagram between these spaces because they don't think in terms of complexes at that point. And so they didn't really define the right degrees of freedom for the space that gets those commuting diagrams. But for us, it all comes out of the one formula. And then for the 2 forms in 2D, you get the discontinuous elements, but there's a indexing change now because PR lambda 2 is 1 higher degree than PR minus lambda 2. And to get complexes now, you have to go on the diagonals up, because the PR spaces, you get, you know, say P3 lambda 0, D of it is P2 lambda 1, and D that is P1 lambda 0. And of course, there are some complexes that mix the slides from this slide, that mix the spaces from this slide and the previous slide. 3D. The 0 forms, you get the Lagrange elements. I think I'm getting tired of saying that. The 1 forms, you get Nedelec's generalization of the BDM elements to H curl. And for the 2 forms, Nedelec's generalization of the H div elements to the BDM elements to H div in 3D. So these are the Nedelec edge elements of the second kind and the Nedelec edge elements of the second kind. And again, the degrees of freedom are now given in this totally natural way that works from the general formula. And we get the DG elements for the last space. And the exact sequences are on the diagonals going up. Okay, any questions? That is the construction of finite element differential forms on simplices. That's everything I know.
Can you explain intuitively why the degrees of freedom give you, with the DG elements, don't appear on the sides?
So several things are coming together here, and they're all sort of fitting together nicely. So one is we have the formula, like this formula here. And so if F is a face of dimension n, the full dimension, so this is the full tet, in other words, then, and now we're talking about the case k is equal to n, then of course d has to be greater than or equal to n. So this formula says you shouldn't put any degrees of freedom on anything lower dimension than the whole tet. So this becomes a 0. And d is equal to n. And so all you do is put full polynomial space PR minus 1 on the tet itself. So in other words, u in PR minus lambda n of t, the degrees of freedom are the integral over t only. There are no other ones of u wedge q, and q would be a PR minus 1 lambda 0 of t. And notice two things. These are n forms, these are 0 forms. They're both just scalars. So these are polynomials, and these are polynomials. For n forms, PR minus is PR minus 1. So this is just PR minus 1 polynomials. These are just PR minus 1 polynomials. They're really the same thing. The vector proxies are the same thing. So this is just saying, take a polynomial degree R minus 1 and put all the degrees of freedom in the center of it. Now you have to do that because in n form you can't integrate over a lower dimensional face. And if you weight it with something, you'll only get higher dimension, not lower. So n forms, the only thing you can do with n forms is integrate them over volumes. Okay? N forms are densities. You can integrate a density over a volume and get a meaningful number out of it. So when we draw these pictures, the point of the picture is if a symbol is on a vertex, that means that's a degree of freedom associated to the vertex. If a symbol is on an edge, it's associated to the edge. If a symbol is in the interior of the domain, it's associated to the tet. So I tried to draw all the symbols in the interior for those ones. Certainly in 2D, it's very clear. I put all my symbols in the interior, say there's no degrees of freedom associated with here. And by the way, if all your symbols are in the interior, it doesn't matter what they are, because the thing, really all you care about is the span of the degrees of freedom associated with each face, and here it's 0 with every face except the interior where it's everything. Okay? Now the other thing that comes together is h lambda n is just L2, and so we're trying to find finite elements who have enough continuity to belong to L2. They don't have any d's that have to apply to them, so they don't have to have any continuity. Any other questions? Holger. So that's a very interesting subject, non-simplicial meshes, and if I have time, I'd like to talk at the end about the recent work on differential forms on cubic meshes that Gerard Awano and I have been working on. So I will claim many times in the next day and a half that the two natural God-given spaces of differential forms on simplicial meshes are PR and PR minus. And we know two spaces which also appear to be God-given and maybe are the only God-given ones, but we're not sure, on cubes. And other shapes, there's not much that's clear except when you can use a tensor product construction. Yeah? it's a good question. I've sort of gone around that without being very explicit. So let's take the case of the gradient first. So the question was, what does the business mean about your in space h lambda k, where d is well defined with degrees of freedom? How are those things connected? So suppose you have, let's say, two triangles, and so you have something that's equal to shape function u minus here and the shape function u plus here. That's our function u. Take zero forms first, just ordinary functions. And we want to know, is u in h lambda 0, which means the domain of the gradient, which is another way to say, if you take the gradient of u as a distribution, is this an L2? Okay? Now u is piecewise smooth, so even think in one dimension. Let's say we have a function that's equal to one polynomial over here and another polynomial over here. Let's say that's u. Well, I would say this u is not in the domain of the gradient of the derivative, because if we take the derivative of this, we get the derivative of this on this piece, plus a delta function at the interface, and delta functions are not in L2. So this is not in the domain of the derivative, while this one is in the domain of the derivative. Its derivative is whatever it is. I can compute a derivative. Its derivative is some discontinuous function because it's not C1, but it's an L2 function. Right? And so what I'm getting at is that a piecewise polynomial is in H1 if and only if it's continuous at all the interfaces. Otherwise, when you take its derivative, you'll get a delta function at the interface. Okay? You with me? Okay. Now, suppose we go to H lambda 1, H curl, or in 2D, H rote. Then you have a piecewise polynomial vector field over here, and another piecewise polynomial vector field over here, another polynomial vector field over here. So that's u minus and u plus. They're both vector fields, and the question is u is the rotation of u in L2, the scalar curl of u. Okay, the way you answer those questions involves integration by parts and the definition of the weak derivative. The answer to the question is if and only if u minus dot t is equal to u plus dot t on the common edge E. So if the tangential components match up, you can take the rotation. Otherwise, you can't. If the normal components match up, the divergence will be in L2. Otherwise, you'll get delta functions on the edge jumps. So as an example, okay, so the space H lambda 1 contains piecewise polynomials whose tangential components agree at the interfaces between triangles, who have no tangential jumps, but they're allowed to have normal jumps. And the degrees of freedom we impose are on the trace on the edge. The trace of a one form on the edge is its tangential component, and we put enough degrees of freedom to make sure those traces are continuous. That's why on each of the slides, the second line in the theorem was the imposed continuity enforces inclusion in H lambda k. There are enough things about the trace of u on edges to make sure that the trace of u is actually continuous from one side of the edge to the other, and therefore d of it makes sense. That's okay? Let me make a small computation here that also might be helpful. Let's write down a function that's not continuous, but it's in the domain of H lambda k. And at the same time, we'll write down a basis function for P1 minus lambda 1. So P1 minus lambda 1 on a two-dimensional triangle, which is vector proxy is Ravi-Artoma lowest order elements in the rotated form. Okay, so what I want is a function on this triangle whose tangential component u dot t is equal to 1 on this edge, and u dot t is equal to 0 on this edge, and u dot t equals 0 on that edge. That's a basis function for the shape functions there. It has this degree of freedom equal to 1, and the other is equal to 0. Okay, well, u dot t is 0 on this edge means that the function will be purely normal in this edge, and normal on this edge. So at this point, it has to be 0, because it has to be normal to two directions. So it's 0 here. And here, the tangential part shouldn't be 0. So it can't be normal, so maybe it's something like that. And it's linear on the edge, so it's going to be something like this, where this is going to increase linearly. On the other face, it's something similar, where we have something like this. It has to be it has to be normal on this edge, so it has to be something like that. Except it's going to be up, actually. It's going to be something like that, and it's going to increase linearly on this edge. And it's also linear on this edge, so between here and here, it has to linearly have a linear thing. So we have this sort of thing that's basically flowing through a flow that looks like that. That's the basis function for the Raviart-Thoma space. Now take another triangle and do the same thing. That'll be basically flowing like this. The tangential component along these edges of these two things will agree, but it looks like that at that point. So the tangential components both agree. They're both equal to that, but the normal components are quite different. It jumps. But since the tangential components agree, we can take the rotation of this thing. Yeah? You take the negative of them. They're not the sign is not determined. So we have to orient each of these edges to decide when we say t, do we mean this or do we mean that? That's totally arbitrary. Okay? So when I say that the u dot t is single valued, of course that's if you use the same t on this side as on this side. Otherwise u dot t is a negative as you cross it. But any other questions? Okay. So now I just want to put together, we had a theory that said, okay, I guess I have to say something about projection. No, I said something this morning. We have a theory that says if we have subcomplexes with bounded cochain projections, then we can apply our abstract convergence theory. And we're basically there now. We've defined the spaces that we're going to use. And we have to verify the hypothesis a little bit and then interpret the conclusions of the theorem. But we've done all the hard work. Except that in verifying the hypotheses, there's the technical issue I spoke about this morning, which is the degrees of freedom define projection operators onto these spaces, but they're not bounded projection operators. And so there is this technical issue of smoothing and so forth. But putting that aside, then we have shape functions. They combine into de Rham subcomplexes. Then when we assemble them together, then instead of having this on each t, we have it piecewise. So we have it on th. So we have finite elements that form nice subcomplexes. And the degrees of freedom give us projection operators. Because of Stokes' theorem, they commute with d. If we suitably modify them with this technical smoothing business, we get bounded cochain projections, and so our abstract theory applies. And we can use any one of these complexes that we have. That is, we can use say in 3D, these four complexes, an nd 2 to the n minus 1 complexes. But after all, when we solve the Hodge Laplacian, we only need two spaces from these complexes. And the third space, the one right after, we use sort of for theoretical purposes. So we could take any of those choices. And for the first two spaces, it really means you could either take PR followed by a PR minus 1 or by a PR minus. Or you could take PR minus followed by a PR minus or followed by a PR minus 1. So you have four choices to solve the Hodge Laplacian. Okay, so for example, if you want to solve the one-form Hodge Laplacian, let's say the two-form Hodge Laplacian in 3 dimensions, lambda h lambda 1, h lambda 2, which is h curl h div. Here you could use PR minus lambda 1, or you could use PR minus 1 lambda 1. And if you use PR minus lambda 1, you could use, actually I think I would prefer to do this differently. Here you could either use PR lambda 1 or PR minus lambda 1. If you use PR lambda 1, you can either use PR minus lambda 2 or you could use PR minus 1 lambda 2. And if you use PR minus lambda 1, you can use PR minus lambda 2 or PR minus 1 lambda 2. So you have four choices here. And they all work. The theory applies to all of them. If you're at one end of the sequence or the other, it reduces down to two choices. And if you're just solving the zero-form Hodge Laplacian, there's only one choice, the Lagrange elements. So you have these four choices, and they're all allowable. And so we know that these are all stable choices. We know you get best approximation in the norm that combines the sigmas and the u's together. And then we have our improved error estimates. And the improved error estimates, well, remember we had these terms, best approximation plus some etas and h's. So you have to go through and see what rates of convergence you get. And well, that depends on how smooth your data is and how much elliptic regularity you have, so how smooth your solution is, and what degree of complete polynomials you have in your finite element spaces. So maybe that's a good point to make, that if we're in PR lambda k, and we're looking at u minus v, where v is in the best approximation in PR lambda k, then this will be order hr plus 1, because we have polynomials of degree r there. And if we're looking at du minus dv, then it'll be order h to the r, because d of this only has complete polynomials of degree r minus 1. Well, if we're at PR minus lambda k, then the first one, this doesn't have the full polynomials of degree r, so this will be only order h to r minus h to the r, not r plus 1, and du minus dv will be also order h to the r, because d of this space and d of this space are the same. So you work it all out and you just check everything, and it basically says if you have smooth solutions, every single component that you're interested in, u minus uh, du minus duh, sigma minus sigma h, and d sigma minus d sigma h, all of these are as good as the best approximation in the subspace allow. In other words, they agree with what these things say here. So all four of the possible choices lead to optimal order approximation in all four of the norm quantities written here, if you have smooth solutions and elliptic regularity. And if you solve the eigenvalue problem, you get convergence as order h to the 2r for all these choices. So you've got all the estimates that you would hope to have in a basic finite element analysis. And I'll end with some historical notes, and then I think we'll call it a day. So I've mentioned several times that the lowest order case of the PR minus family, P1 minus, That's the one that's so geometrical. 1 degree of freedom per vertex for 0 forms, 1 per edge for 1 forms, so on. That was, because it is so geometrical, it was actually invented by the geometer Hassler Whitney, and it's in his very difficult but incredibly insightful book, Geometric Integration Theory from 1957. And Alain Boissevit, who's an electrical engineer at Électricité de France, realized in 1988 that what the mixed finite element people were doing and what the Whitney had done in his book were really the same thing. So he said that mixed finite elements are Whitney forms rediscovered. Only the lowest order mixed finite elements is that true about, however. Then, in 1976, there was a paper by two geometers, Joseph Dodzuk, who's a professor at City University of New York, and Vijay Patodi, who died in the year of this paper at, I think, 29, age of 29 or something. Tragic, because he was clearly brilliant. They were trying to solve a problem from topology. So there's something called the torsion of a manifold, and there's more than one way to define it. And one way, which I think is called Franz-Reidemeister torsion, is very combinatorial. You put a simplicial complex and you do something combinatorial with it. And another way has to do with eigenvalues of the Laplacian. And the question was whether these things were the same. And they aimed to prove it by doing a discretization of the Hodge-Laplacian on the manifold using finite differences and showing it converges. So they had a plan of attack for the Ray-Singer conjecture. And so they wrote a paper about a finite difference approach to solving the Hodge-Laplacian, and it was strongly influenced by Whitney and Whitney forms, because that was the kind of stuff they knew, not finite elements. And their method took this form, find U defined on, let's say if we're doing one forms, defined on the edges, such that du dv, or dhu dhv, plus d star hu d star hv equals fv for all v. But how do you define these dh and d star h if you have something on edges? So that's where they used Whitney. They said, well, Whitney says if I have numbers on the edges, I can extend it and get a real differential form and just take the real d here. And that'll give me sort of a matrix operator from numbers to numbers. That'll give me a matrix that represents this guy here. And for this, I'll take the transpose matrix, basically, for d star. And then they tried to analyze this. They thought about it as a finite difference method, and they tried to analyze it. And they had a hell of a time, because of something I mentioned briefly before, that this is not, if you think of it as a finite difference operator, is not consistent. This is a bit of a crazy operator. They didn't realize that this could also be thought of as a mixed finite element method. It would have been much easier to analyze. But there are hard workers and smart people, and they got a convergence of eigenvalues of order h log h. And all they needed was convergence. It really should have been h squared, but all they needed is convergence. They got it. The rest of their proof of Ray-Singer didn't quite finish it, so they didn't get the Ray-Singer conjecture, but then a guy named Werner Müller in Germany 2 years later continued on this work and proved the Ray-Singer theorem at around the same time that Jeff Singer gave an independent proof of it, Jeff Cheeger. So there was actually people doing mixed finite element approximation, although they didn't know it, they thought they were doing finite difference approximation of the eigenvalues of the Hodge-Laplacian in '76, completely unknown to the numerical analysis community. And this kind of idea also appears in the work of Dennis Sullivan, and he used what we call now the PR lambda K space. He used space of piecewise polynomial differential forms with the right interelement continuity. In the finite element world, the first person to say, hey, maybe it's a good idea, maybe Boissevit really has something here, to try to think about these finite elements in a uniform way using differential forms was Ralph Hipmeyer, and he gave a very seminal paper called Canonical Families of Mixed Finite Elements, where he treated the PR minus spaces in a uniform way. For example, with the degrees of freedom I showed today. And then when we wrote the ACTA paper in 2006, That was the first time we realized the importance of the Kazul operator, which cleans up what Hipmeer does, and allowed us to also in a uniform way do the PR spaces and the PR minus spaces and see their interplay. There's this nice interplay because the PR spaces are the degrees of freedom for the PR minus spaces and vice versa. So it's a nicer theory when you consider them together. Mark?
Did Sullivan know about the Kazul complex?
I don't know whether they had that. I don't know the work of Sullivan so well. What I know is he used the space of differential K-forms, which are polynomials of degree R on each element, and which have the right continuity to be H lambda K. I doubt he defined it through degrees of freedom. That wouldn't be one of his tools. Sullivan, by the way, when he heard about this, invited me down to his place, and Dojuk is there too. And it was interesting. They brought in 13 graduate students and said, okay, start talking. And I just talked for hours and hours and hours. And so I would say, well, this is not a consistent approximation. She said, what's consistent? And I'd explain to her. He said, no, I don't get it. What is this? So the things that to me are, my bread and butter were very, very foreign. Is a very different viewpoint of this, but we're coming to the same place. So it must be the right place to be. And I think that's all I have to say. So why don't we call that a day? Okay.